So we've been representing orbitals in orbital notation as boxes. And let's see, we assigned titanium and vanadium for you to do as homework. I'm just going to do titanium real quickly for you, just to, so you can check what you got. So hydrogen and helium have electrons in the 1s orbital. So we're going to put one up arrow and one down arrow. And I'm kind of, just to make it go faster, I use half arrows, just makes it faster. Means the same thing, okay? So then we've got lithium and beryllium then are in the second primary level. So they're going to be filling orbitals that are in the second primary energy level, and they're only in the s sublevel. So there's lithium and there's beryllium. And then we get over to boron and all those elements between boron and neon, or including boron and neon. They're in the second row, which represents the second primary energy level, so that's 2, but now we're in the p sublevel region. So we got 1, 2, 3 orbitals there. Now we fill up according to what we've called the school bus rule, 1 on each seat or 1 on each box, and then come back and put in the second arrow. Okay? And so that brings us up to neon. Then we go to the next row. The next row fills up in exactly the same way, only now we're in the third primary energy level, represented by the element's location in the third period of the periodic table. We're starting out in the s sublevel region, so sodium and magnesium are in 3s. There's only one orbital in 3s. And then we get to 3p, where we have aluminum through argon, so that's 3p. And we're going to have 3 boxes or 3 orbitals in the p sublevel. So there's aluminum, silicon, phosphorus, and we come back and pair up for sulfur, chlorine, and then argon. So if you had noticed then, when we did neon, that whole primary energy level, all of 2 was full. When we did helium, all of 1 was full. There's only one s orbital in the first primary energy level. There's no p orbitals there at all. So that's full. When we get to neon, the next noble gas, all that's full. When we get to argon, all that's full. And that's what they look like when you get to a noble gas. All of the primary energy level is full. The primary energy level, their highest most energy level, that's called the valence level. So for helium, hydrogen helium, 1s, or the first primary energy level, 1, is the valence level. Okay? For everything between lithium, if you don't have out your periodic table and are looking, you probably don't have a clue what I'm talking about. Okay? This is where you need to use your tools. Okay? If you use your tools, it's going to help. If you look at where lithium through neon is, that's the whole second row. Well, that whole second level is completely full of electrons. Okay, saturated. And then you get to the third primary energy level. That would be for all the elements between sodium. Put your finger on sodium and put your finger all the way over to the right on argon. That whole row there, the valence level for that whole row is 3. Okay. So the highest energy level is the valence level. That's what we call it, the valence level for each of these elements. Now what we care about mostly is the valence level, because that's where all the action takes place. Once we figure out what's going on with electrons and how they fill up, we find out that only the valence level either gains or loses electrons or shares electrons. So that's where all the bonding takes place for all the elements on the periodic table. Now, so now we're as far up as argon. So when we get to potassium and calcium, now we're in the 4th row. And potassium and calcium are in the s sublevel region. So they represent the filling or putting electrons into orbitals in the s sublevel region. And there's only one orbital in the s sublevel region. So this would be orbital notation for potassium and now calcium. And then we get to those transition metals. Okay, so now we're about to start where scandium is here. Okay, and when we get to scandium, the filling order there drops back to the third primary energy level. So we're not going to be filling electrons in those transition elements. The position of those transition elements is such that we're not actually filling electrons in the primary energy level, the valence level. We're filling it back in the lower level. Now, funny thing happens with that, because that third 3D level we're about to fill actually sometimes is involved in bonding. But let's not sweat it right now. Let's just talk about how it feels, okay? So when we start with scandium, we're going to not the 4th D level, but the 3rd D level. And when I showed you that sort of chart last week, where we put that 1, 2, 3, 4, 5, 6, 7 S, and then 2, 3, 4, 5, 6, 7 P, and then D, and then F, that's just a way of being able to follow along which one of these things we hit when we hit it. Does that make sense? And you start, the arrows go upper left, upper right to lower left, and so then you kind of swing back and go up, back like that, okay? On that chart. Y'all remember that chart? If you don't remember that chart, if it doesn't just, isn't clear to you in your head, get it out and look at it. Now's the time to review physically, visually with that, okay? All right, so now we have 3D. When we get to 3D, there are 5 orbitals, okay? So S orbitals, or S sublevels, have only 1 orbital. P sublevels have 3. D sublevels have 5. You see a pattern? No? What pattern do you see? 1, 3, 5. Odd numbers. It's going up in odd numbers. So every time we reach a new sublevel region, we add and we have an increasing odd number of orbitals. 1, 3, 5. So how many orbitals is F going to have? 7. Well, anyway. So scandium is going to have 1 electron. Then we go to titanium, and that's the orbital notation for titanium. Got that? So up to now, we've been talking about orbitals being squares. They aren't really squares. This is a way of inventorying things. If you were taking an inventory in the store, you'd be counting where everything is, counting all the little items and all the shells, and putting it in some kind of list. Well, that list doesn't look like the shells, does it? You're just numbering how many there are on the shelf and keeping up in a kind of spreadsheet of some kind. Well, that's kind of what this is. It doesn't really represent the shape of the orbital. Okay? So what we're going to do today is to start looking at what is the actual shape of the orbital. Well, these S orbitals here, and here, and here, and here, they are all spheres. S orbitals are all spheres. They're all spheres. So if the nucleus is right here, then this 1s orbital is going to be a sphere surrounding, or roughly surrounding, where that nucleus is located. And that 2s orbital surrounds that. And the 3s orbital surrounds that. Just shading to kind of show there's a sphere, not a circle. You don't read enough comic books to know that. Yeah, I'm a big comic book fan. Okay, all right. And then so forth. 4s is going to be around that, and so forth, okay? So these are the S sublevels are concentric, meaning one inside the other, spheres. Okay? Then p orbitals don't have a spherical shape. P orbitals look like a set of 2 balloons. So guess what you're going to be using balloons for today? Okay? Now that's the way we represent them. In reality, there's a little more to it than that. It's like the p orbital is only the top half of the balloon. Okay, if we draw a dotted line right there, that's the actual p orbital. But we can't make 2 balloons that stick together that are sitting out there in space like that, like orbitals can. Okay? So what we're going to do with our balloons is we're going to draw this dotted line around the center of it and label the ends of it for the orbitals, but then we're going to tie them together so they sit in space the way they should. Does that make sense? All right, so this is a single p orbital here. This drawing represents a single p orbital. Okay? If I were to put all three p orbitals, see how they have three p orbitals here and here? If I were to put them all together, and they're going to arrange themselves three-dimensionally. I'm going to have one p orbital like this. Then I'm going to have a p orbital that's coming to the side out here like this. And then I'm going to have a p orbital that's going swinging out here toward you guys and behind the whole drawing. Now, let's see. Front and back. You got it. Coming out toward you like this, and then being back here behind everything. So this represents a set of three p orbitals. Does that make sense? Now those p orbitals are actually arranged inside the s orbital in that same primary energy level. So if I were in the second primary energy level, I have an s orbital and a p orbital. Okay? So if that's the case, then I'm going to have a one p orbital coming out toward you like that. And we'll have the one that's vertical. Then we'll have the one that's going from side to side. And let me finish the one in the back now that I've got everything kind of in front. And then the s orbital would surround all of that. So then this shows what a set of s and p orbitals in the same primary energy level. Primary energy level is the term that I prefer to use, and in the video, the guy fast talking guy in the video called them a shell. Okay, I don't like to call them a shell because they're not really a shell. It's a primary energy level, and a primary energy level corresponds to, doesn't mean it's the same thing, but it corresponds to the elements on the same row of the periodic table, the same family. I'm sorry, not family. The same period on the periodic table. Okay? Families and groups go vertical, periods go side to side. All right, does everybody understand what we're doing? We're only going to make p orbitals today because I don't have any way to put them inside a bigger balloon. You got that? All right. So you're going to need to start with two balloons of the same color, two round balloons of the same color. You're going to blow those up and tie them together, and then you're going to label them. And then we'll do the next set after that, okay?